You ever wonder how databases can feel so, well, instant? You agree, the buffer pool. The buffer pool manager, or BPM for short, is without a doubt the single most important performance part of any database. You should think of it like a huge, really smart cache that lives in super fast RAM. Its one and only job is to be a gatekeeper, to minimize those agonizingly slow disk operations by keeping the most popular pages of data ready to go. And the logic behind it is basically a simple decision tree. When some part of the database asks for a page of data, the buffer pool asks one question first. Do I already have this in my cache? If the answer is yes, fantastic, it's handed over instantly. If no, it has to find an empty spot in memory to load it into. But, and here's the really crucial part, if there are no empty spots, it has to decide which old page to kick out to make room. And under the hood, it's really a team of components all working together. You've got the pages array, that's the actual chunk of memory. You've got the page table, which is like a super fast index for finding where everything is. The free list keeps track of empty slots. And then you have the replacer. Now this is the brains of the operation. The replacer is the component that makes that tough call about which page gets evicted. Okay, but having this super fast cache creates a whole new problem. How do you stop everything from turning into total chaos when you have hundreds of different things trying to happen at the same time? Well, you need a critical safety mechanism. Let's just think through the nightmare scenario. Imagine one process is reading a customer's address from a page in memory. At the exact same microsecond, some other process forces the buffer pool to kick that page out and replace it with, I don't know, product inventory data. What happens to that first process? The answer? Total catastrophe. Without some kind of safety rule, that first process is suddenly looking at complete garbage data. The whole system is corrupted. The solution is something called the pin/unpin contract. Before a process can touch a page, it has to pin it. This is like putting a do not disturb sign on the door. As long as that page is pinned, the system is forbidden from evicting it. Once the process is done, it unpins the page, and it's fair game again. And the rules of this contract are simple, but they are absolutely sacred. If a page's pin count is anything more than 0, it's in use, and the eviction algorithm cannot touch it, period. Just as important, when a process unpins a page, it has to tell the system if it changed the data, if it made the page dirty. A dirty page has to be saved back to the slow disk before that memory slot can ever be reused. Okay, so we've got our safety rules. We know we can only evict pages that are unpinned. But among all those available pages, how do we choose which one to kick out? This decision, this is everything when it comes to performance. Yeah, this really is the million-dollar question. The cache is totally full. We absolutely have to bring in a new page from disk. That means we have to make a sacrifice. Out of all the unpinned pages just sitting there, which one gets the boot? Now, the first thing that probably pops into most people's heads is a policy called Least Recently Used, or LRU. And the logic seems, well, perfect. Just find the page that's been sitting around unused for the longest time and kick that one out. It just sounds like common sense, right? Well, for a database, this common sense approach is an absolute performance killer. Just imagine someone runs a huge report that has to scan a gigantic table. This single query reads thousands and thousands of pages, one after another, and none of them are really important or likely to be used again soon. This scan completely pollutes the cache. It floods it with temporary junk, and, using the LRU logic, it kicks out all the truly valuable pages, like critical indexes that the database needs all the time. Performance doesn't just dip, it completely falls off a cliff. So clearly, LRU is a no-go. We need a smarter, more resilient strategy. So let's look at the incredibly elegant solution that protects the database from this exact kind of disaster. What we need is an eviction policy that is scan-resistant, one that doesn't get fooled by these big, loud, one-off queries. And that is exactly what the clock algorithm gives us. Some people also call it the second chance algorithm, and you're about to see why. The way it works is surprisingly simple. Imagine a clock hand that is just sweeping across all the pages in the buffer pool. When it needs to find a page to evict, it just looks at whatever page it's pointing to. Case 1, is the page pinned? If so, we can't touch it. Skip it, move the hand. Case 2, is it unpinned but has a little reference bit turned on? This means it was used recently, so it gets a second chance. We just turn that bit off and move the hand. Case 3, the hand lands on a page that's unpinned and its reference bit is already off. That's our victim. That's the one that gets evicted. And that simple second chance is the absolute genius of this algorithm. The pages that are truly important, the hot data, they get accessed so often that their little reference bit keeps getting flipped back on. They're constantly earning another chance. Meanwhile, all those thousands of throwaway pages from that big scan, they get their bit turned off. And by the time the clock hand sweeps all the way around again, they haven't been touched. They've lost their second chance and they get evicted. It perfectly protects the valuable data. So, we've gone pretty deep into the technical weeds here. Let's pull back up and connect all these details to the snappy, instant performance we all expect from modern software. So what's the bottom line here? The key takeaway is that the responsive feel of a great database isn't an accident. It's the result of all these layers of really clever engineering. The buffer pool is the magic trick that hides the slow disk. That pin/unpin contract is the non-negotiable guarantee of data safety. And as we saw, the common sense solution is often dead wrong, which is why smart scan-resistant algorithms like Clock are absolutely essential for stable performance. Truly high-performance systems are just full of these kinds of elegant, non-obvious solutions. And that really leaves us with a final thought to chew on. The whole problem we explored started with what seemed like a totally logical idea, least recently used. But it had this hidden, fatal flaw for this specific kind of work. It really makes you wonder, doesn't it? What other obvious technical solutions that we all rely on might be hiding a similar critical weakness, just waiting for the right conditions to show up?